Good morning, ladies and gentlemen. I'm going to talk today about towards. I think I've used the word towards because I think this is going to be a long project. So it's starting to try to set some form of a systematic methodology for designing elevated traffic. And I also like to use the word traffic systems to distinguish between traffic and engineering. So generally in our area we have traffic design, we have engineering design, and engineering design could include electrical and mechanical. So trying to look at some form of systematic methodology for design. So I'll talk about aims of this project. I'm going to distinguish between rational rules and rules of thumb, and I think that's an important distinction. I'm going to put some suggested structure of the system. Now this is the tricky bit, extracting knowledge from the experts. And I'll talk about that process. I'll also talk about historically how we've actually designed by trial and error. There has never been a discipline in history, in science and technology, where we had the rules laid out and then we started the proper design process. It's always been an iterative process. There's nothing wrong with that. That's the way technology advances. I'm going to show you the rules, but to be honest, my role today is not to tell you what the rules are. That's not the important bit. The important bit is to sell you the methodology. I want to sell you the concept. And I'll finish with an epilogue about some books. So the aim of this project is to develop a systematic procedure, a systematic set of steps that someone can follow in order to come up with a design. It's only a first part of a series of papers. Now, I do assume that we already have a building block which is beyond the scope of what I'm talking about. We have a building block which does the design of a single zone building. That's beyond the scope of what I'm talking about. Just imagine a blob or something where you can refer to that blob and do the design of a basic building, a 24-floor building. Let's assume we do have that. We can go back, go to it, get the design, and come back. That's sitting inside. We're going to actually overarch that. And we have to have a set, I'm calling them crisp to distinguish them from fuzzy. So all of the rules I'm going to show you today are crisp rules. If A is more than B, if A is less than B. I'm not going to use the expressions, although admittedly that's how experts think. They think is if it's much larger or it's much smaller or larger, smaller, or nearly the same. These are the sort of things that fuzzy thinking involves. I'm not going to that. We're looking at crisp rules at this stage. As I said, we assume we have a basic design tool, a calculator and a simulator. Now, the other thing is eventual software will actually prompt, suggest, query the user or the designer at every stage of the design process. That's where lots of systems fail. They're trying to force on the designer an outcome. They're not explaining the output. If the designer or the user feels he or she is in control, then they can actually change things, override suggestions, accept, modify. So these are the three words: prompting, suggesting, asking. It will also be nice if a software suggests back to you why they've made that decision, like an expert system as opposed to a neural network. So they'll tell you, I believe these are the reasoning for my recommendations. That's not there yet. This is just all some ideas, but the rules are ready. So the designer can then override and accept. I need to put two important points here. I'm not by any stretch of the imagination suggesting that I'm an expert in this field. There are other people who have that expertise. I'm really acting as a data miner. And this is an expression used in computer science a lot. People who go in and they extract the knowledge and so on and try to build this and put it in a... So, I've approached a number of experts, three of whom are here today. I apologize to others. I'm sure there are other experts here in this room. And I apologize if they haven't been involved, but they will be involved in future stages. The other point is, and this is the point I will actually reinforce a number of times, is that we don't wait for the theory and then go do the design. In most of the science, you look at the Watts engine, the Watts governor, Stevenson engine, many areas where design has proceeded and then theory has actually followed, and then it became an iterative process. Of course, you will tell me there are lots of buildings which are already designed. That's correct. But that doesn't stop us from actually trying to capture some of those rules in a crisp and clear format. So we're doing that retrospectively. Okay, what is a rational rule? As opposed to a rule of thumb, a rational rule actually clearly explains what the performance criteria on which it is based is. So if that performance criteria does change later on, you can actually change the rule. The danger with a rule of thumb is that it is embedded. The rationale is embedded. So you would say for every 100, for example, 100 lifts, for 100 occupants, we have 1 lift or 2 lifts and so on. The danger with that is the assumptions are hidden. Now, they are in the mind of the expert. That's why we need a rational rule as opposed to a rule of thumb. I like these examples from fire engineering, and Adam or others maybe can confirm them. For example, a nice example on selecting the speed of a lift for firefighting is the 60-second rule. The lift must travel between terminal landings, including delay for acceleration and jerk, in 60 seconds. And there is a rationale for that. So for the firefighter, he can get to the point within a certain period of time. Another nice one, which depends on the length of a hose. If we have a fire hydrant on a floor, then any point on the floor must be accessible, must be within 60 meters of that fire hydrant. So these are nice rules, rational rules, which you can see the rationale behind them, the reasoning behind them. Okay, so looking at the structure of a system, let me skip this and go to the structure right away. So we have the user designer working with an interface. Now, these are the two pieces, the tools which we have for calculation and simulation, and I think we've discussed this in previous symposia. Most people, the majority of people, will start with a quick calculation. They'll do a quick calculation to give them the ballpark of what they're looking at. And most of them then will move on to a simulation to see, to look at other parameters and so on. So we're assuming that these two pieces exist for a basic building block. Now, there's where the rules will sit on top of that design interface. So the design interface will query the rule, come back to the user or the designer, suggest something, prompt something, go back and so on, and keep on using the rules until we get to a certain design. This is the most difficult part. We obviously have human experts in all spheres of science and technology. They have an accumulation of years of experience. They're very good, obviously, at what they do. However, they usually find it hard to encapsulate that knowledge in a clear rule. They have so much knowledge, but it's so difficult sometimes to extract that. Why do we want to extract that knowledge? Well, I'm arguing that if we don't capture that knowledge, it's going to be impossible to advance and mature that corresponding area of science and technology. So we need to expand it in order to pass on that knowledge into future generations. Otherwise, what you will have to do is to have someone sit down next to the expert, shadow him for 5, 6, 7 years until they can get that knowledge. Then it's also impossible to automate the process. You can't automate a process unless you have those rules. Approached a number of people. As I said, I apologize for others if I haven't approached them, but I got responses from Maria Lisa. Joachim is here today. Hans, John Carroll. Jorg is not here. And I think Adam and also Peter Sumner here. Yeah, so, but as I said, this is a long project, so hopefully we'll approach others along the way. Fuzzy logic is an excellent example. I've only talked about crisp rules up to now, but fuzzy logic is an excellent example where it's even more difficult to extract a fuzzy rule. And the knowledge from the experts is extracted as a set of fuzzy rules rather than crisp rules. And it just goes into everything today. Many items, many devices we use today. Washing machines. How soiled is the wash? how hard is the water, what temperatures can I use, and so on. And you start using these terms. It's very soiled. It's somewhat soiled. The water is very hard. The water is very soft. The water is soft, and so on. And with all of these rules, you can actually build up decisions. Air conditioners, even things like bank loan decision making and project management risk. It started with cement kilns in the 80s. That's where it was quite successful. I think in a Norwegian group, they extracted the rules by watching an operator. And the operator was just operating and changing different parameters. That's with cement kilns. I think 1980, 1982. And there are so many parameters you can set, but you have a set of rules, fuzzy rules to set them. Washing machines now. A lot of washing machines use fuzzy logic, and even rice cookers. So now the other question is, which comes first, theory or practice? And I wanted to mention this. We had a long discussion with John last time. Do we really need to go into that detail, into the theory, if practice is there? And I'm going to give you some examples from history. The history of science and technology is an iterative and incremental. You'll agree. It is incremental. There are big steps, but it was quite iterative along the way. We moved from theory to practice, back and forth. Best examples, Lee Gray is here, North Carolina. The Wright brothers, the first mechanized flight. When they started, they didn't have much on aerodynamics and so on. They did a plane, they tweaked it, they got it to fly. Look at the improvements from that time to now. Watts governor, the steam engine, and the design of aircraft structures. In fact, control theory really took around 100 years to mature to what it's matured now to. Just been reading a nice book. That's that book there. It's very accessible, very nice. It gives you an overview of control theory, how the history of it, how it's developed. It's no equations. It's just a general book on the history of control. That's another good example as well. This is the Tacoma Narrows collapse, bridge collapse. Every student on system dynamics and control theory starts with that. Nothing focuses the mind like a thought of execution. And this is a phenomenon called resonance. It started, I think it opened in June or July. In November, the winds got so strong that it caused damage, significant damage. You can see the deviations are increasing with time. There was nothing wrong with the bridge design as such, statically. It was there was a dynamic problem. Galloping Gertie, I think they called it. Okay, quite significant damage. Obviously, all you need today is a bit of damping. You need to increase damping in the structure. We also had something on the Millennium Footbridge. Anyone saw that? Now, it wasn't but people felt uncomfortable at the time. Another good example, actually, metal fatigue. This is the Comet 1954, 2 fatal crashes, and it turned out the square windows were a problem, because a square window would actually be a stress concentration point. It increases the stress so much that it initiates a crack, and then the crack goes through a fatigue, because every time you pressurize the cabin and depressurize it, that's a cycle, and then you get quite significant or quite fatal results on there. So that's another iterative theory and practice cycle. I'm emphasizing this because I know what people will say. People will say, why do we need this if we've got buildings designed? I'm not arguing with that. I think we just need, theory has to keep on feeding practice. Okay, let's have a look at the 6 rules, the 6 crisp rules. Now, the interesting thing is sometimes we invoke these rules at the calculation stage, and sometimes we invoke them at the simulation stage. And that's specified in each one of the rules. That's another, a simple rule, for example, we all know it, the 8 lifts or 12 lifts as a maximum in a group. Now, to be honest, that is still a rule of thumb. And it needs to be changed into a rational rule. Because the reasoning for 8 is it takes you time to walk from where you're waiting if you don't know which lift you've been assigned until you get to the lift. So really make it rational. We should have said something like, if it takes you more than 3 seconds, it shouldn't take you more than 3 seconds to walk from where you could be standing in the lobby to the lift and get in. So really that's still a rule of thumb, but at least that's the start. The second one is about zoning. If the traveling or transit time, as the correct expression is, if it exceeds a certain limit, usually you need to zone. That's a trigger for zoning. Rather than saying, if you have 20 floors, more than 20 floors, you zone. That's the rule of thumb. This is the rational rule. It says what the reasoning for it behind it is. And that's an example for zoning. I call this actually a direct from ground system. And that's a luxury we have, but we only have it at low rises or relatively low rises. A direct from ground system, you have one single journey to get to your destination. So you either take this group and you get to a destination, or you express through here, you get to a destination, or express through here. At some point, that luxury becomes unsustainable, and you have to have sky lobbies. We need a trigger for that. We need another rule, a rational rule for it. So the third rule is, for example, splitting the zones to equalize the number of elevators. The fourth rule is, in some cases, you might have a too small a car, and you're getting queues developing, but everything else is fine. And one of the solutions in that case is to increase the car capacity. Now look at the rule. I tried to use a sort of standard format. Jonathan will correct me on that. An antecedent. So this is the condition. You check the condition, and if that condition is right, then you carry out whatever is here, or else you do something else. Fifth rule, this could be a trigger for double-deckers. Admittedly, we're just doing it by trial and error. We would say this building is suitable for double-deckers, this building is not suitable for double-deckers. This could be used as a rational rule for triggering or using double-deckers, which is the car capacity. If you do calculations, you find the car capacity is large, everything else is fine. That could be a trigger for double-deckers. And the sixth rule, I think one of the most important rules, it starts saying, when do you trigger sky lobbies? And my argument is you trigger sky lobbies when the area you're using in the building becomes excessive. And I used the figure of 1 to 4. Other people could actually use different figures. So to clarify that, this is, for example, this is a trigger for sky lobbies. You get to a stage where you start using a sky lobby. And the reasoning is it becomes unsustainable. The building becomes unsustainable. And I've taken here a fictitious building, started increasing the number of floors, and you see there's a cutoff point, there's a threshold here, which is 1 to 4. We exceed 1 to 4. So we're using 1 meter for every 4 meters of net area, 1 meter for the lifts. So to conclude, we've suggested the 6 rules. They've been rational rules. And as I said, we aim to suggest, explain, and prompt rather than force an outcome. There's an interaction with calculation and simulation. Then we apply the rules. And as I said, I think the reason sometimes these things fail is because they try to force an outcome rather than interact with the user and cooperate with him or her. Next steps. Really, the next steps now, there's still much more work to be done. We're taking a larger number of buildings and trying to test the rules with a larger group of experts. Okay, I'm just going to finish with another book. All of this smacks of automation. We had a discussion with Richard on this. Are we trying to automate the process? Well, I'm not really, but I've been reading this book, and I thought I'll share it with you. It's called Rise of the Robots, Technology and the Threat of Mass Unemployment. A guy called Martin Ford. Is the book, very nice read. It's, he paints a very pessimistic and bleak view of the future with automation, robotics, and artificial intelligence. Some of it is maybe a bit far-fetched, but there are lots of interesting issues in there about automation and so on. So if anyone is interested, they can come and have a look at the book. And I just finish with a quote. A little nonsense now and then is relished by the wisest men. Thank you very much.